And now I can't find my, good grief. I can't find my, there we go. There we go. Got it. Okay. We are now live. Yay.
Yay. Howdy, Richard. Susan Bruce says, okay, is this song about negative charges forming matter that is destructive? Don't know, Susan. Maybe. We'll have to find out.
There's my brother.
Well, hello, everybody. This is Scott Roberts and Dr. Daniel Barth here, and we are on it's the 29th.
29th episode.
Yeah, great. So we're in the second part of Dr. Barr's dissertation on dark matter. And
Indeed.
I think you're going to really enjoy this one. If you had time to download the study guide, you would really be able to dig more into it. I do recommend that maybe even right now you go to the link that's in this post and download the study guide, and also download his book on astronomy for educators. It's free, and so it's great to check it out. We have a great week lined up for you with the 70th Global Star Party starting tomorrow, and we can talk a little bit more about that towards the end. But right now, I'll recognize some of the people that are watching. We have Richard Grace. He signed on first using the official greeting, which is howdy. Susan D. Bruce is watching. We have Pekka, who's imaging the sun as we speak, and enjoying that out of Stockholm, Sweden. Andreas Villarreal says hello, and Harold Locke is watching. We have Andrew Corkill watching out of Southern California. Susan D. Bruce says, I'm sorry, Facebook, scrolling and haven't studied any science in a while. Okay, well, you're going to get your dose today.
You're here, so you're forgiven.
Yes, that's right. Pekka says the sun looks great and have nice sunspot groups right now.
Awesome.
My sister's watching, so hello, Teresa. And Andrew Corkill says it's raining in Southern California. Matthew McCallie, yes, says hello everyone from Mississippi. So greetings, Matthew.
Welcome.
Yep. And Martin Eastburn from East Texas, he's watching as well. So anyhow, and Rodney Cox is watching as well. And for all of you that aren't chatting with us, hello to you too. And so we're going to get started with Daniel Barth.
Hey, Scott. Good to be back again. And some really exciting news in astronomy. We had something this month that has happened only twice. It's only been recorded twice. Now, how many times it's happened and how many times it's actually been recorded, that's two different things. But for the second time, we had a meteorite pierce someone's home. Wow. And for the second time, it came through the roof of a single family home, this time in England. The last time was in Louisiana. And the last time was in, I don't know, the 1940s. And the meteorite, about a 5-pounder, bounced around the room and hit the woman in the thigh, almost broke her leg, bruised her very badly. This time it came down and it smacked into someone's pillow. So, inches from tragedy, but, and punched a hole clean through the roof. The woman talks about hearing the huge bang and things seeming like rocks in a can bouncing around in her room, and then being able to look up through the roof and see the stars. And so a meteorite actually punctured her house and hit her bed inches from her head. A miracle that she survived, uninjured. But it's kind of an amazing thing. And this meteorite, like the last one, bit bigger than your fist, about the size of a cricket ball or a baseball for our American friends, and shows this was all over the web, but the meteorite actually landed on her pillow, probably after bouncing about the room a couple of times. So crazy stuff. And it's interesting. Last time my students were out and we were taking a look at the moon, and the full moon was rising. And I mentioned to them, they watched the full moon rise over the horizon at my ranch. And I mentioned to them that it's kind of unique that you get a chance to actually experience the cosmos in motion. Most of us go out, we look up, the sun's up, the moon's up, there are stars out, and we don't watch long enough in order to perceive any motion. And I said, it was a full moon night last week when the students came out. And so sunset was at 6:25, moonrise was at 6:26. And I said, oh, well, okay, we are standing on the edge of the Terminator. If you think about the line that divides daylight and darkness, I say we're standing on the edge of the Terminator. We've got the sun, we're facing south. We have the sun sinking on our right. We have the moon rising on our left. And the rotation of the earth is carrying us across the Terminator into darkness as the moon rises. And the kids were all, they all had a great time, and we photographed the moon. We got some very nice photographs, just smartphone through a refractor, and challenging to get a good photo of the full moon with a smartphone. Very bright object on a very dark field, but we did. And so the astronomy class and the astronomy program, Scott, continues to go swimmingly. We've had such a lovely fall and so many opportunities for observation. Oftentimes, as you know, in Arkansas at this time of year, someone throws the switch and the days go from balmy and clear and sunny to dark, gray, cloudy, and lots of rain. But we've had good observation nights. So I hope everyone in the audience has been enjoying that. And we're going to take a look at our dark matter. Now, of course, you know, Scott, that I have friends in low places all over the world. And so I coordinated with Sky and Telescope. Not. But I was so thrilled.
They coordinated with you, I suspect. So
yeah, I went down on Friday afternoon. I'm like, oh, the new Sky and Telescope is here. And I looked and, oh, gee, what's the main cover photo? It's Henrietta Swan Leavitt, you know, the discoverer of dark matter. I'm like, holy cow. And, you know, she, almost along with Vera Rubin, helps discover dark matter. I'm like, this is awesome. And she's known for Leavitt's law. And the idea of the standard candle and the Cepheid variable. She didn't discover Cepheid variables, but she did do some other research. And we'll talk about her in a bit, but encourage everybody, pick up the new Sky and Telescope. That's got some great stuff in it. And we're continuing to adapt these lectures from the 4% universe by Mr. Panic. And that's also highly recommended work. So we're going to start today with someone who kind of an amateur in astronomy. She's, you know, she started out, gee, I want to be an astronomer, but she really struggled to make her entrance into astronomy. And we're talking, of course, about Vera Rubin. And she was in middle age before she got any time on a, you know, professional class telescope. Of course, professional class telescopes are nice, but I like to remind our audience that time and again throughout history, discoveries have been made on telescopes of 0.5 meter aperture or less, and tremendous work has been done. But Rubin, basically, one of the things she found is that coming up in the 50s and 60s is that trying to be a woman in science was difficult. And she, is a matter of just career path choice, she time and again decided to pick areas without a lot of people in them. There were areas where there was lots of competition and there was lots of people already working there. And she found that occasionally she would have difficulty making her way and making her name in groups like that. And so she would pick little out of the way areas. And discussing with my astronomy for educators class this last week. And I said, well, yeah, how do we know when we look at a theory, how do we know when a theory is performing well? How do we know when a theory is performing badly? And if it's performing badly, how do we know when it needs to be fixed or thrown away? Which is not a small issue. And one of the things we discussed, theories are never perfect. Scott, and we've talked about this before.
That's right.
The science is never settled. We're never done investigating. And in fact, it's when we look at a theory and the idea, the philosophical ideal of a theory, it's a set of ideas and explanations that explain everything we know about a particular topic, whether that topic is stellar evolution or black holes or anything else. A theory is usually a lifetime work by an individual, or more often today, a working group of individuals led by a few really brilliant people. A theory is something that's a lifetime achievement that gets you in textbooks. And facts are kind of simple, hard, trip over them in the dark sort of things. And we talked about this. We talked about theories. How do we know when a theory needs mending? And I tried to point out to my students, I'd like to point out to our audience, that when we're researching a theory, when we're crafting a theory and we say, oh, it's like the last few pieces of the puzzle. If you're like, during the pandemic, everyone was working on the cardboard, the multi-piece, 500-piece puzzles. And so often you get down and you realize, oh, there's a piece missing, or you've got a piece that's an odd color that doesn't seem to fit. It's these bits that don't fit that really, really point us in the direction we need to go. Mm-hmm. I tell my students that when you're looking at a theory and it all seems to be from a distance, this nice, smooth, polished edifice, and then you get closer and you start looking, oh, here's a crack. Through that crack, investigating that area where things don't fit, that's the doorway to new discoveries. I said, if you're going to get a Nobel Prize, that's where you'll find it, in one of those cracks, in one of those places where things don't seem to fit. And so Vera Rubin decided to take up, people were looking at the Big Bang and other things, and Vera Rubin said, well, let's look at individual galaxies. Hubble did it, worked okay for him.
Yeah.
And so she decided to work on proper rotation of galaxies. And she actually made a big stir, the very early 60s. She said, I'm going to take a look at proper motions of galaxies. And she said, well, gee, planets rotate, solar systems rotate, galaxies rotate, and galaxy clusters seem to rotate. So if I took a look at proper motions of galaxy clusters and large numbers of galaxies, would I in fact see that the entire universe rotates or not? She did this work basically on her own, and when she went to the American Astronomical Society and gave her presentation, it was highly controversial, and it gained her a lot of fame, but caused her a lot of grief. And there were a number of people who were like, no, this is an interesting idea. Just because you didn't think of it first doesn't mean it's bad. And so she was looking at this and she said, gee, does everything have a rotational state? In fact, further work has shown that idea is a non-starter. There's not a...
So the whole universe is...
There's no evidence that the universe as a whole rotates. And in fact, that would have been really exceptional. It would have been the first time in 500 years that anyone had found a violation to the Copernican principle. And we've talked about this before, the Copernican principle. Copernicus basically said, no, the Earth is not special. We're a planet like the other ones. We don't occupy a special place in the universe. And what came to be known as the Copernican principle over many centuries, the idea that if your data shows that you found a special place, a special motion that makes you unique in all the universe, you're almost certainly wrong. And no one has found a violation of the Copernican principle to date. And if the whole universe was rotating, there would have been a central axis.
Right.
Or if it was all just random orbits around a gravitational center, it would have said, oh, there's a center of mass to the universe. There is a special place. And Copernicus is, And so this research garnered her a lot more detractors than it did admirers, but it did show original thinking. And after this whole business with does the universe rotate, she basically decided to find a new research partner. She was looking at people were working on Big Bang and cosmic background. She said, no, that's not for me. This field is too crowded. And so she partnered up with a fellow named Kent Ford. Kent Ford was developing a new technology, the photomultiplier tube.
Oh,
now,
okay.
all of us who have smartphones with cameras on them, we all benefit from Ford's idea. And the old night vision is basically a photomultiplier tube. But for us with modern sensors, those of us who are astro imagers, we have CCD and CMOS sensors that we image with, and we can dial the ISO up and down, which basically means we can tune the sensitivity of the sensor. And general rule of thumb is if you make the sensor more sensitive, if you jack up the ISO, yes, you get a better sensitivity. You pick up faint things, but you get more noise. So there's always a trade-off with these things in an engineering sense. But back in the day, 1963, astronomers are still basically taking photographs on film with film at the prime focus of a telescope. In 1963, virtually no one is using an electronic sensor at that point. The electronic sensors are in their infancy, and they're just not very sensitive. And Kent Ford says, oh, you know what? When we're taking the spectra of a galaxy, what we're basically doing is we're moving along and we're looking at a very small point we're not taking the entire picture, we're taking a small point, we're using a diffraction grating. If we're just picking up a few photons anyway, wouldn't it be nice if we could multiply them? And basically his idea is he's got a charged plate, one photon hits and it creates a cascade, a shower. This is much like the way cosmic radiation, the high energy gamma particles hit our atmosphere and we get this shower of particles down through the atmosphere. Mm-hmm. And Kent Ford basically finds a way to build a mechanism for this. And so
now, how much of a leap was this? I mean, I think you make mention in your guide about the length of time that it took to get the spectra of a galaxy for the first time versus how long it took to get spectra in 1963. Is that right?
The first spectra were taken about 60s? 1916. So back in the era of Charles Lamplin and et al., right? And Percival Lowell and all those folks who were developing astronomy. The first spectra is taken in 1916, 84 hours of exposure.
Ooh, okay.
I know. And it's like, oh my God. And he did this over a 3-month period.
Yeah.
So
we have amateur astronomers doing 84-hour and 100-hour.
I'm imagining he's using something like a 12 to 16-inch refractor, right? Yeah. Big reflectors were not common back then. Right. The Sproul, which you and I have had a hand in, is a 24-inch from 1911, and it was at the time the biggest in the world. There were a couple of them that size. Yeah. So you're talking about an aperture of less than 300 millimeters and 84 hours. And you realize that had to be a single plate. There's no image stacking. So this person, Francis Pease, he's taking a single plate and he's pulling the shutter off of this thing. And okay, I've got 2 more hours. Close the shutter because the clouds are coming in. And you take this plate very carefully and you put it away. Yeah. Because I'm sure he's not the only person using, one of the world's biggest
so your odds of screwing up the image are
right. And so he's got to keep aligning it perfectly.
Yeah.
It's just the mechanical precision of this is just phenomenal.
It's insane.
By 1963, things are a little better, mostly because of film technology. Right. We knew about hyperring film. We could use chemical treatments. We could make film more sensitive. And telescopes were a bit bigger. By 1963, you could get yourself time on a 48 to 60, maybe 100-inch telescope. But the spectra that were being taken on the 36 and 48-inch telescopes in 1963, you're still talking tens of hours,
Wow.
10 or 20 hours over several nights.
Wow.
Yeah. So I want to reserve the telescope for 3 nights. I'm going to take the spectra of Andromeda, and I'm going for a 20-hour exposure with the plate locked in there. And it's kind of like, holy cow. Not only that, but they're taking pretty much the whole spectra at one time. And of course, the film, as you know from Film Day, Scott, film sensitivity is not the same. It's not even over a spectrum.
Yep.
And so I'm sure they were getting that much, they were probably overexposing some of the green and yellow in order to get some of the blue and red where the film was less sensitive.
Mm-hmm.
And so they're doing this crazy stuff. Well, Ford's photo multiplier is letting them take 10 spectra per night. So he's getting spectra in less than an hour, where before it was taking more than 10. So he's improved things by, a factor of 20.
Right.
So, and this really is one of the first electronic images in the history of astrophotography. I'm sure there were some other people experimenting, but this is basically, and he custom built this thing.
Yeah.
And Ruben talks about, packing this thing up in the trunk of a car and hauling it with its power supply and everything to an observatory, Kitt Peak or wherever they had time. And they would unpack it and spend the day mounting it to a telescope and getting it all ready to go. So as darkness fell, they could use the photo multiplier tube and get their hours of exposure. Well, Ruben is really excited. We're getting spectra. And so she has this, here's an idea. Here's something nobody's doing. And I read her work and I read her commentary and I read interviews. I'm really not at all certain she was looking for something. I'm pretty sure she was not looking for something that was new and different and amazing. She was looking for something where she could work unmolested and publish and pursue her career. She's a mom by this time. She has several children, and her husband is being Mr. Mom when she's out traveling to observatories. He's also a physicist. And so she basically says, well, okay, back to this idea I had about everything rotates. She said, we've got these spectra now. We can actually get spectra, not just of a galactic core where it's bright, but we can get spectra of regions farther out. And hello, Doppler shift. And so I'm going to go ahead and share a screen with our viewers. And here we are. And so we see this lovely Doppler shift, and this is in the program guide, which I hope you all will download. And here's a galaxy. Yes, again, wonderful art by Dr. Barth. And so we see here's a galaxy with its spiral arms, and we see that we have an approaching arm, we have a receding arm, and we realize that the signal from the center should be unshifted, because it's not moving with respect to us, or if it is, it's really quite slowly compared to the rotation speed. Yes, Andromeda is falling toward us, but very, very slowly compared to its own rotation. And so you get this unshifted signal, this pure signal from the center, which allows you to have a baseline. And then you can measure the approaching signal, which should be blue shifted, as those stars and emitting portions of Andromeda are rushing toward us. They compress the light wave. You can see I've taken care to make our wave coming towards us here with a shorter wavelength. The amplitude is the same, but the wavelength is not. And you get a blue shifted signal. Now, we all know that, how can you tell if the light is red or blue shifted? Well, what we're looking for is spectra. and spectra has Fraunhofer lines. Fraunhofer, the German astronomer and physicist who built the first equatorial mount. Yes, the German equatorial mount is a Fraunhofer. And he's also the fellow who discovered absorption lines in the spectra. And he did it in spectra from the sun. And he and Bunsen, he of the Bunsen burner, they realized that, oh, various elements, if they're vaporized, if you vaporize oxygen, chlorine, nitrogen in an electric arc and you shine a light through it, those elements will absorb certain frequencies. And so you're, instead of having a smooth, coherent rainbow, red, orange, yellow, green, blue, indigo, violet, you have dark lines. And these dark lines are places where the elements have absorbed things. So you're looking for things like hydrogen, oxygen, carbon, phosphorus, silicon, common elements in every star system. And so the galaxy has fingerprints. And the fingerprints should be in a certain location. But in fact, in a blue shift, the hydrogen spectrum is shifted. Hydrogen is in the deep red spectrum. It's shifted more towards the red-orange part of the spectrum. Blue and violet stuff gets shifted out to the ultraviolet. And so everything gets shifted the same amount toward the blue. And that has, when you measure this blue shift, you get a very precise determination of how fast that portion of the galaxy is moving towards you. Same way on the receding side, that signal shifts toward the red side of the spectrum. And so Vera Rubin is expecting, oh, the amount of red shift should equal the amount of blue shift. In other words, the galaxy should be rotating at one speed in any given place. The other thing she's looking for, Scott, is she's really looking for something called a Keplerian distribution. If we take a look at this, again, we're going to back up a little bit, and we find out that, oh, Kepler's laws of planetary motion. And we'll have to do a program on Kepler one day. We haven't done one of those yet. Kepler's laws, Kepler basically says the square of the radius is proportional to the cube of the period, which I won't bother to go into the numbers on that, but basically what it amounts to is the farther away you are from the center of mass, the more slowly you orbit. So Pluto is 40 times farther away than we are. If it was a straight linear relationship where we take 1 year to go around, Pluto would take 40. It doesn't work that way. Pluto takes 248 years to go around. Jupiter is 5 times farther than we are, takes 12 times as long, 12 years to go around. Saturn takes 29 and a half. Uranus takes 84. Neptune takes 165, and so on. And also, as you get closer, Venus orbits the sun in just 8 months. Mercury in 88 days. And so Kepler deduced this law. And Vera Rubin says, well, galaxies have a center of mass, just like a solar system does. And so we're expecting this Keplerian motion, which means that as we move out from the center of the galaxy, we should find that everything is rotating more slowly. And we should find, if we plot the distance and the velocity, the angular velocity, we should get this nice curve that tends to flatten out. Well, Vera starts taking spectra at different portions, just incrementally moving out from the center on Andromeda. First on the blue shift side, then on the red shift side. And it's all wrong. It's all wrong. And so basically, she's looking at this. And again, I'm going to go ahead and share a screen. What she's finding is something very odd. She's expecting this Keplerian orbital curve. And we see here's Jupiter, Saturn, Uranus, Neptune, Pluto, and we see this lovely curve that continues but never reaches flatness, but it continues to. And then there's the galactic orbital curve, which Vera Rubin and Kent Ford are getting. And by golly, it's just flat, which means everything from the center out to the edge is going around in the same amount of time. And so instead of being like a Keplerian orbital curve, galaxies act more like big LP vinyl records. If you put an LP vinyl record on, the whole thing travels as one piece at one speed. So if it's 33 RPM or 45 RPM or whatever it is, the whole thing travels at one speed. Now, what used to flummox me as a kid is I sat there and I realized, oh, wait a minute, the outer songs, and maybe you remember looking at old vinyl LPs and the tracks, and you could see the tracks and the gap between them on old-fashioned albums. And you realize that the skinny tracks on the outer edge held more music than the fat tracks on the inner edge.
Right.
And you realize, oh, okay. So as I go in, well, it's all traveling at the same speed, but there's not as much length. The track isn't as long because it doesn't have as big a radius. Well, Vera Rubin said galaxies act like LP records. Everything travels around at the same rate, center out to the very edge. And so this crazy non-Keplerian curve, and everybody is just banging their heads and saying, it can't be true, it can't be true, it can't be true. And once again, Vera Rubin finds herself as the center of controversy, where everybody is saying, you screwed it up, it can't possibly be the correct answer. Your data is wrong, 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 because it doesn't fit our theory. And of course, I'm going to throw him out there again, Sherlock Holmes, Arthur Conan Doyle. We must twist theories to fit facts, not facts to fit theories. And so they're all making the capital error, as he would say. They're all making the capital error. And so what's happening? Well, they're doing this work. And as Ford continues to improve his photo multiplier, they're actually able to move out beyond the visible edge of the galaxy. They're looking at stuff which is way out, invisible, it's too dim to see, but we know gravitationally it would be orbiting around, kind of like the Oort cloud in our own solar system, too far away to really see. We know it's there. We know it's held in place by the sun's gravity. Well, they're looking at stuff all the way out. The curve is still flat, and it's nuts, and it's driving everybody crazy. Well, about this time, this is by now the mid to late 60s. And Jim Peebles, who we've met before, cosmologist, and he's doing some work. And basically, the question is bugging him and it's bugging other people. Why do we have galaxies anyway? Now, one of the ideas today is that what you're actually looking at, galaxies are little quantum fluctuations that were there in the early universe. And as we had the Big Bang and then the inflation period, the quantum fluctuations caused areas of high density and low density. That's why we have galaxies. And the Wilkinson anesotropic microwave cosmic background, the WMAP Explorer showed the variations in temperature. And so, yeah, we know this now, but they didn't know it then. So the question is, gee, if the universe should have been isotropic and homogeneous, in other words, the idea says, well, isotropic, it should look the same no matter where you are or which direction you're looking in. It should look the same in every place. It's kind of like a universally dusty, dirty floor. It's the same in every corner. Out in the center, it's just universally messy. And there's no big clumps and no big structures. Homogeneous means that it's basically the same throughout its volume everywhere. Well, these ideas come along. So Peebles is now working with some of the first supercomputers in 1969. These would have been the very biggest, baddest computers of the day. considerably less technology than you have in your breast pocket in your smartphone right now. Considerably less technology than you have on your desktop or laptop or tablet. But in 1969, it was the big thing. And he basically started out with 40 particles. Give them a distance, give them a mass, common center of gravity, let it start rotating and see what happens and see how it clumps up. And Peebles is able to show, oh, look, we get these lovely galaxies, and eventually gets up to we can have 2,000 points, yay! And it forms this lovely spiral structure. And another young guy, Jeremiah Ostraker, comes up and he says, Jim, it won't work. And Peebles says, why not? And he says, well, look, I'm working with water droplets. You talk about macro to micro, right? We're talking about galaxies, structures of 100,000 light years wide and trillions of solar masses of material. And here's a water droplet smaller than a millimeter. And Ostraker is basically using sound waves, and he's making the water drops rotate. Because the water droplet is several trillion molecules of water, right? So it makes a pretty good simulation of a galaxy. And he says the problem is that as it rotates, it tears itself to pieces. So once again, we'll share a screen and we'll show you here what Jeremiah Ostraker showed. And what he showed was that as these water droplets would start to spin, they would indeed form this lovely flattened disk, as you would expect, as we see now with forming planetary solar systems, disks of dust and gas around a forming star. And then eventually it forms a bar, and we see barred spiral galaxies. But Ostraker says the problem is that more and more material flows out of the center and into the ends of the bar. And eventually, because of moment of inertia, the bar cannot hold itself together. Water tension, which on this scale is a much more powerful force than gravitation. Gravitation is really weak sauce. These water droplets break apart. They form a disk, a bar, and then they split apart into two or more droplets. And so Ostraker is now taking a look at galaxy photographs. And he said, you know what? Every galaxy we see, it should either be in a bar shape or it should have broken to pieces by now, because he's noting that it takes about 5 rotations. Once you form a bar, you've got about 5 rotations, and then the whole thing goes kablooey and comes apart into pieces. And the Milky Way has had a chance to have at least 20 rotations by now. So is Andromeda, so is Triangulum, so is all these galaxies that we see. They all formed at a certain period in the early days of the universe. They've all had 15 to 30 rotations, plenty enough. So why do we have big galaxies at all? Ostraker says, you know, the only thing that works, he says, is if there is some hidden mass. If there's a much larger amount of mass than we can actually see, then it would have enough gravity to hold these galaxies together. But if we're just basing it off the luminous matter, the galaxies are like 90% too small. They need 10 times the amount of mass that we can see to make them hold together. And it's called the missing mass problem. Well, it turns out as they do their research, Peebles and Ostraker find out that they are not the first people to figure this out. Fritz Zwicky, who is a Dutch-American physicist, did his work in Caltech in the 30s and 40s. He was looking at galaxy clusters, and he noticed the same problem. He said, they're spinning too fast. They should be flying apart. And in his native Dutch, he refers to this, and I'm going to, for those of you in the Low Countries, I'm going to massacre the pronunciation. Please forgive me. He calls it dunkle materie, or dark matter. And he says, we can't see it. It's not emitting any radiation that we can detect, but it has to be there because we're seeing the gravitational effects. So there's this dark matter. And so Peebles and Ostraker go ahead and they say, okay, well, if there's matter we don't see, let's go back to Jim Peebles' lovely galaxy simulation and let's put mass in there in different places and see what works. No matter where they put it on the interior, it doesn't give them any kind of a result that matches what they see today. The only thing that works is if the galaxy exists within a spherical halo of dark matter, much like the Oort cloud, which is believed to be a spherical shell which surrounds our solar system. And so, gee, could there be a halo? And they run a bunch of simulations and they find, hey, look, they find the size that works and the mass that works, and it matches up with Fritz Zwicky's prediction of the missing mass is at least 90%. And furthermore, Peebles and Ostraker find out that if you make the halo too big, if it's too small, if it's too close, if it's too far away, it doesn't work. As Goldilocks says, it has to be just right. And so if this is some kind of a feedback system that creates the halo and trims it up to the right size or beefs it up to the correct size, what is that mechanism? In other words, how does the halo know where to form or how much dark matter to put there? And we don't know. We don't know. Well, now by about 1973, Rubin and Ford are coming back and they're looking at all the galaxies in our local supercluster, and they find out they're all falling in towards a common center of mass where nothing appears to be there. There's no dust cloud, there's no collection of galaxies, there's nothing that they can see. And by the way, we've looked at the dark attractor. It doesn't give off the X-ray signature of a black hole. And so people are now pissed at them again. You're predicting crazy crap. Why should the galaxies all be falling towards something that's not there? And they're calling this the Rubin-Ford effect. And people that love them call it the Rubin-Ford effect with a hooray in their voice. And people that hate them call it the Rubin-Ford effect, as if it's some kind of Donald Duck, Mickey Mouse cartoon thing. So by 1974, Rubin and Ford are able to get some time on the 4-meter telescope.
Cool.
And they're looking at galaxy clusters, and they're finding, just like galaxies, galaxy clusters also have flat rotation curves, which is driving people crazy. By this time, you know, they've been gathering data for 10 years. A lot of other people have been gathering the same data. People don't really dispute this idea of the flat rotation curve anymore, but people are just like, it doesn't make any sense. And so we find by many paths, dark matter leaves footprints. Saw an article very recently, the oldest human footprints ever discovered so far were found on the island of Crete, and they predate the African footprints in the Rift Valley in Kenya by about 2 million years. And so this is pushing back hominid evolution by a couple of million years. And like these footprints, and what did these people look like? Did they look like us? Probably not really. More simian? Probably. But do we know? No, because all we have is this footprint in the sand that is hardened and becomes sandstone over millennia. And so it is with dark matter. We have these footprints in the sand that are fossilized there. And we can see the footprints, but we can't see what is making them. And the difference is the hominids who were in Crete and in the Rift Valley in Kenya millions of years ago, 4 to 6 million years ago, well, guess what? Dark matter is still here. it's still making the footprints. And we can see it in the way galaxies rotate, in the way clusters rotate, in the way galaxies and things fall in towards an seemingly empty center point. Something is out there in the dark. Now, people have tried to find dark matter particles. They've talked about WIMPs, weakly interacting massive particles. Our Oort cloud material would work as a WIMP. Some people say, well, it must be a subatomic particle. The machos, the massive compact halo objects. And so are they subatomic? Are they massive and visible? Is there really like a cluster of cometary sort of material out there that's 10 times the mass of a galaxy? We don't think the Oort cloud has anything like 10 times the mass of our solar system. But obviously something is out there. And this is kind of the bleeding edge of modern astronomy. So if we go much farther, Scott, we're going to just go into a lot of speculation, and I wouldn't be sharing actual data with our friends. And so I really can't go farther than that. Do we have any fun questions or anything from our our visitors in the comment section today? I'm not hearing you, sir.
Yeah, there was the question about, of course, where we have dark matter. Is there anything other that would be considered light matter other than visible light, or within
the idea of dark versus light matter, all the common baryonic matter, which is the stuff that you and I and the stars are made of. The idea is that we all radiate at some frequency. Thermal radiation, infrared, give off radio waves. So even stuff that we don't normally consider to be bright matter, like plasma in star systems, the dust and gas emit in radio and infrared frequencies. And that's part of the excitement. The James Webb Telescope is going to be an infrared telescope. And when I first heard about that idea 20 years ago, I'm like, nah. But no, it turns out to be really cool. Infrared radiation travels through dust clouds without being blocked,
right,
the way visible light does. And so it should be able to see farther back in time, farther away in space. And so the Webb will be astonishing.
Right.
It really will.
So here's another question from Splash Autumn watching on YouTube. Splash says, how can we make it possible to detect dark matter? Has there been an experiment set up to directly detect it, or is it always just something that's inferred that it's there?
There are a number of dark matter detections. There's one called Satori, Satori, which is being conducted with the American and Canadian governments. And it's in a mine in Canada. And this is very similar to the neutrino detectors, Scott, if you're familiar with them.
Yeah, like where you have rays hitting like a vat of lens cleaning fluid or something.
Right, exactly. So they have these massive ultra clean pools in the bottom of mines a couple miles down in mountains to screen out all background radiation. And they basically have a tube in the dark, and hello, Kent Ford, photomultiplier tubes surround the inside of this giant swimming pool of fluid, with the idea that if dark matter does interact, it will cause a certain. Various theories say, oh, well, if you've got this kind of dark matter and it does interact with a regular particle of matter, it will cause this sort of interaction, will produce these particles, this sort of radiation. And so they're looking at these sorts of experiments and seeing if they can give the knockout punch to certain theories, because we've talked about this before, Scott. Science is a destructive process. Thomas Kuhn and Karl Popper basically say, yeah, it's a cage match with broken bottles and baseball bats, last man standing. And so scientists, a great number of scientists, spend the majority of their career trying to shoot down somebody else's theory. Because if I can shoot down the other guys, if mine lasts longer, I'm the last man in the cage and I win. And so they're doing these experiments with the idea that, oh, if we get certain results, some theories may be eliminated. We're narrowing the idea, if we can narrow the parameters. The ice cube experiment, sensors buried in glaciers, a kilometer deep in glaciers in Antarctica. These are looking to do some detection of dark matter. And so there are these deep sensors that are looking for very subtle interactions, and we have to put them far underground to screen out all the everyday interactions that gamma rays, cosmic rays, background radiation would have with normal matter. And so we're trying to get as quiet an environment as we can, so we can pick up these very, very faint signals. To give our viewers an idea, when the supernova 1987A went off in the Large Magellanic Cloud, the two working neutrino detectors, one in Japan, one in the Americas, detected 11 neutrinos.
Yeah, 11.
11, plus one, yeah. 11, that many, 11 neutrinos from, and the number of neutrinos passing through, your thumbnail or the tip of your nose, trillions per second. But neutrinos interact, and neutrinos have been proposed as dark matter. There may be a type of neutrino that is a candidate for dark matter. So there's a lot of theories and a lot of attempts to detect, but they really don't interact with normal matter very much. At any given time, the sun is pumping trillions of neutrinos per cubic centimeter through your body at all times, day and night, because the Earth is not a barrier. They shine right through the Earth with no problem. Straight through.
Right.
And you realize if they interacted with your body, you would be fried like an egg. That much of any other kind of radiation passing through your body would just destroy you. Life would not be possible. But life is possible because the neutrinos don't interact. They are weakly interacting. And they're not WIMPs because they're not massive particles, but there may be a species of neutrino. Remember, the dark matter has to have a gravitational effect. And neutrinos, like photons, virtually massless. So they're not a good candidate, but there may be some neutrino-like particles that may work. So it's kind of cutting edge stuff.
It is. Well, just like researchers and theoreticians and experimenters will continue to set up things to try to directly discover dark matter. I'm sure that once it's done, somebody's going to get a Nobel Prize.
Absolutely.
Right.
And well earned.
Right.
Could be like the Higgs boson. Do you know the Higgs boson paper? Higgs was the first. He was the primary author. Okay. 1,600 co-authors.
Wow.
Yeah.
Yeah, so it's not just a couple of guys coming up with. So
the first three lines share a Nobel, and the rest of you, thanks for playing. Yeah,
that's right.
You get the home game edition of How Do You Know?
That's right. Yeah, but I imagine that at one time, we already imaged a black hole. Who would have thought that? I really did not think that would be done.
I never thought
in my lifetime.
No,
so
never.
But the rate of which scientists are able to make discoveries now is just incredible, and
it's amazing.
So it may hopefully before this chapter of our lives or whatever our existence or whatever.
I want to live long enough to see boot prints on Mars. That's my. I want to be.
Yeah, there you go.
We've done it.
Right.
Anyway, you've given me a great segue for next week's How Do You Know topic. We're going to turn away from the galactic and we're going to rein it back in and come back home again. And we're going to take a look, and we've talked before, Scott, about how people are famous for making small corrections and small adjustments to theories. We're going to take a look at this idea once again.
Okay.
And we've taken a look at it before. We've said, Einstein is famous because first man in 350 years to make any correction to Newton. And Leonard Susskind, bless him, and the Black Hole War, 35 years to prove Stephen Hawking was wrong about a casual statement made at a conference. We're now going to look at the big impact theory, which is kind of interesting because the half-life of great theories seems to be getting shorter
Hmm.
as the pace of discovery gets faster. And the big impact theory of planetary formation, Scott, this is within our lifetime. When we were young, this wasn't a thing. And after the Apollo missions, we said, oh, you know what? The moon could have been formed by a single impact by a Mars-sized planet called Theia. And this could have caused a big splash, and the splash could have formed a ring. From the ring, the moon, and so on, the whole creation story. And we've seen lots of evidence of big impacts in the solar system. Well, now there's somebody coming up and saying, you know what, we need to tweak that. And they've come up with a really interesting variant on the big impact theory that they call hit, run, and return. And so it sounds like a mob hit, right?
Yeah, it does.
Hit and run, and then come back and give them another shot. So it sounds like something out of The Sopranos or The Godfather. And we're going to revisit just how violent the early solar system was. And so we're going to take a look at the latest iteration of the big impact theory next week on How Do You Know?
Great. Looking forward to it, Daniel. All right. And so for all of those people who love to watch Dr. Barth in these programs, definitely look him up on his Facebook page on How Do You Know? And what other, I have most of the links on your page on Explore Scientific.
The Astronomy for Educators Facebook page.
Right.
And this goes for anybody who wants to learn more, as well as who want to teach. We've talked before, Scott, about the idea of a telescope is a party in a box. You open it up and people think you know stuff. If you own a telescope, you must be smart. Tell me this. And so the Astronomy for Educators YouTube channel, lots of fun videos there. And the Astronomy for Educators, which I wanted to call Astronomy for Everyone. But they said that wouldn't reach the right audience. I think it would have. But Astronomy for Educators, and the new book, Star Mentor, we're going into our final edit phase, which woohoo, thrilled with that. So I'm hoping that we'll be able to announce that Star Mentor will be reaching bookshelves near you sometime next year. Cross our fingers, knock on wood, and hope that the publishing process is smooth. So yeah, and anybody who has a question or wants to reach out to me individually, astronomyforeducators@gmail.com. And I'm always happy to take queries from astronomers and teachers and students of the dark arts. So
yes.
It's Halloween. I had to slip that one in there. So there you go.
All right. Well, thank you very much.
Exalt the powers of darkness.
Yes.
Right? There you go. Telescope in hand. Anyway, Scott, there you go. And
all right. Well, thank you so much. It was wonderful to be back with you again, and we'll see you again next week.
We'll see you next week, everybody. Thanks, and bye-bye.
Bye-bye.
Why do we chase this thing? Jumping from one continent to the next, just to bathe for a moment in the absence of light? Who are we? What are we searching for?
T.S. Eliot wrote, "We shall not cease from exploration, and the end of all our exploring will be to arrive where we started and know the place for the first time."
One of the qualities of seeing an eclipse is it makes you understand that every given thing is in a particular patterned relation with every other thing.
It gives me a sense of scale, gives me a sense of where I fit into the universe.
It is art, it's poetry, it's this kind of experience of going and seeing totality in which what feels merely metaphorical is suddenly experiential encounter.
Immediately afterwards, you have that overwhelming desire to see another one. That's the moment an eclipse chaser is born.
These are folks who are running all over the world for this event that lasts all of 2 or 3 minutes. Who are these people?
It's unique each time. And therefore that freshness, even if we've seen it over and over again, oh my gosh, it has the potential to re-inspire us.
A total eclipse of the sun doesn't just unfold in the heavens. It transforms the minds and hearts of those who experience it firsthand. The same is true of journeys to the most remote regions of our planet. Whether we're standing on a mountain peak or in a stark polar landscape, we can't help but reflect on our place within the larger scheme of things.